So far we've looked at forces, we've looked at vectors. Today we're going to put it all together and figure out how do we use vectors in describing forces. So about as simple as I can make this is, let's take a look at a book sitting on a table. Think about what are all the forces that are acting on this book, and how could we make that into a diagram that we can start looking at the vectors. Let's look at that example of a book sitting on a table. So if we look at a book sitting on a table, we have a table here, and we have this book just sitting there. If we think about what are all of the forces that are acting on this book, well, we know that there's one force, which is the force of gravity, which is going down. I'm going to call that F sub g. What's another force that's acting on this? If it's just gravity, the thing's going to accelerate downwards, but it's not. We have the table pushing upwards. And we actually have a name for that force. We learned about it in a couple of lessons earlier. We call it the normal force. I'm going to call that F sub capital N for normal force. These are the two forces that are acting on this book. Now, there's forces like air pressure and different things, but we'll kind of ignore that for right now. If we want to draw this in terms of a free body diagram, we want to draw these vectors as simple as possible. So let me show you how that works. I'm going to draw an object or something to represent the book. I want to make this as simple as possible. What is the simplest thing I can draw to represent any object? Well, you might say like a circle would be good, or a square, and then we could draw forces from that. But really the easiest thing to draw is a dot. So in a free body diagram, you actually start all of the forces from the dot. Now I know that when we first talked about vectors, we talked about the head to tail method. The head to tail method does still work for forces. You can still do it that way. But it doesn't quite make it as easy to follow as you do if you look at a free body diagram. A free body diagram, what we're going to do is we are going to draw all of the forces coming from the dot. So in this case, we're going to draw the force of gravity. We'll call it F sub g, going downwards. And we're going to draw the normal force going upwards. And I did my best to try to make these forces about the same length because they're going to cancel each other out. In this case, gravity is canceled out by the normal force because the book is not accelerating. This is an example of a free body diagram. Let's imagine the situation of a car moving down the street. We're going to draw a free body diagram to represent all of the forces that are really important in the motion of this car. So what we're going to do is we're going to take a dot, which is going to represent the car. So I'm going to start with a dot right here. And I'm going to draw all of the forces coming from this dot that are affecting the car. One force that pretty much always affects things on Earth is going to be the force of gravity. So I'm going to draw a force going down there. Notice that I have an arrow, and we would call this F sub g. Sometimes I just call it mg because really the force of gravity is equal to mg. And that just reminds me that m times g is the force of gravity. So if you ever hear me say the force of gravity is mg, it's really just like saying ma, but that's just, I don't know, I guess that's how I do it. Another force that's acting on this would be the force that's going upwards. We call that the normal force. So we have a normal force pushing upwards as well. What other forces are acting on this car as it drives down the road? Well, we have the force of the engine. The engine and the tires, as they're turning, are pushing the car forward. So we're going to put a force here. I'm going to call it force E, so force of the engine. And it doesn't really matter what I label it in terms of a subscript. I'm going to put an E so that I remember that that's the engine. The last force that would be acting on this would be all of these slowing down forces, the friction, the air resistance, all of these forces that actually slow the car down. And I'm going to put that back here. I'm just going to call it the force of friction. We'll call that friction for right now. These are the forces that are acting on the car. Now, looking at a free body diagram, we can start to make some decisions about what's going to happen with this car. If the car is not going up or down, then we know that the mg, or the force of gravity, is the same as the normal force. And they kind of cancel each other out. So do we really care about either of those? No, we can ignore those. And really the only forces that will determine whether the car is going to speed up, slow down, or go at a constant rate is going to be the engine, and then all of these slowing down forces, these forces of friction and air resistance and things in the engine. If the engine is bigger than friction, the car is going to speed up. If friction is bigger than the engine, the car is going to slow down. If they're the same, it's going to move at a constant rate. The total force acting on the car, the resultant force, remember the word resultant means the sum of all of the vectors. The total force actually has a special name. We call that the net force, or F net. You got to think about like money. Like you have a gross income, which is all the money that I make, and then you have a net income, which is all the money I make minus the taxes and Social Security and all the things that they take out of it. That's my net. It's the sum of all of the pluses and all the minuses. So in this case, we have a plus and we have a minus going in the x direction. We have a plus and a minus going in the y direction. The net force is the sum of all the forces. The actual movement of the car, the total movement of the car, which one of these forces do we need to look at if we want to see what's actually happening with the car? Well, all of the forces are important. So which one of these is the actual, includes all of those forces? The net force. The net force is going to determine the acceleration of the car. So you could say an F equals ma for the total acceleration of the car is based on the net force. So what you're going to find with a lot of these problems is you're going to find that you want to determine the net force. You want to determine what that force is so that you can determine what's going to happen in the situation. In order to do that, you need to draw a picture, or you need to draw this model of a free body diagram. So we draw the free body diagram. We kind of look at what forces we can ignore, what forces cancel out, and then we can simplify it to say, really simplified, if this goes away with that, then the force of the engine is going that way, the force of friction is going that way. If that's bigger than that, it's going to accelerate. So we would say that the net force is equal to the force of the engine plus the force of friction. Well, truly friction is going to be negative, so you're going to end up subtracting the two. This is how we're going to solve a lot of these problems. We're going to find the net force, and then we're going to figure out what happens in the situation. Or, of course, you can do it backwards. Maybe I'll give you information about the situation, like I'll give you the acceleration of the car, which you can then find the net force. If you also know the engine, then you can then find how much friction is opposing this car. So there's lots of ways we can use free body diagrams to solve problems. They're going to be an integral part of what we continue to do. In the next couple of lessons, we're going to look at some examples, specific examples where using a free body diagram is necessary in order to solve a problem. Work through your worksheet. If you have any questions, be sure to let me know, and I will see you soon.